For this question, we are given this equation over here. We are supposed to find the set of values that y can take. In order for us to have a better grasp of what this question exactly requires of us, what I've done is I've sketched a graph that represents this equation. And what this question basically wants us to do, right, it is to find the set of values of y, okay, which is going to be from here to here and here to here that correspond to the curve. Okay, so one way, okay, if there were to be no restrictions at all, in order for me to find this set of values of y and this set of values of y, I just need to take out my graphing calculator again, find the coordinates of the maximum point and the coordinates of the minimum point, because the values of y that this curve can take will simply be y that is less than the y coordinates of this maximum point and y to be bigger than the y coordinates of the minimum point. Okay, but what this question wants, okay, it is for us to solve for this without using a calculator. Which means that I'm supposed to solve for this algebraically, and in order for me to do that, I'm going to pull this concept from our secondary school, where it is the concept on discriminant under the quadratic equation. Okay, to do that, I'm going to introduce a line, a horizontal line that is supposed to cut this curve at least one point. Because as long as this horizontal line, okay, I'm going to call this line y is equal to k, okay, as long as this horizontal line cuts this curve at least one point, this horizontal line which is y is equal to k will have a value of k that is going to correspond to those set of y values that the curve can take. Okay, so this curve here, this equation here, I'm going to call it equation number 1, and this I'm going to call it equation number 2, and I'm going to solve this simultaneous equation with the ultimate goal of having a set of values that is going to, a set of values for x that is going to have at least one solution, because this line and the curve, they have to meet at least one point. Okay, so I'm going to let equation number 1 be equal to equation number 2, solving the simultaneous equation. Okay, so it is x squared plus x plus 1 divided by x minus 1. This is going to be equal to k. Reorganizing this, it is x squared plus x plus 1 is equal to kx minus k. Okay, shifting everything over to the left hand side, this is this plus 1 minus kx plus k is equal to 0. I'm going to reorganize this so that it looks like a quadratic equation. Anyway, it is already a quadratic equation. Okay, so this is 1 minus kx plus 1 plus k is equal to 0. I'm changing into the ax squared plus bx plus c is equal to 0 form, and this will allow me to bring in discriminant, because I want this equation here to have at least one solution, because I want this curve, this line and the curve to meet at least one point. So in order for this, which is going to represent the x coordinate of the intersection between this and that, to have at least one solution, I'm going to let the discriminant be bigger or equal to 0. Okay, so b squared minus 4ac, 1 minus k squared minus 4 times 1 plus k, this must be bigger or equal to 0. We're expanding this, it is going to be 1 minus 2k plus k squared minus 4k is bigger or equal to 0. This is k squared minus 6k minus 3. This is bigger or equal to 0, and I need to factorize this in order for me to solve for the range of values for k. One good way that I would recommend is to apply the completing the square. So complete the square for this, it is k minus 3 squared minus 12. This is bigger or equal to 0, which I can simply just treat this as if it is k minus 3 squared minus square root of 12 squared is bigger or equal to 0. Okay, so with this a squared minus b squared form, we can just apply the a minus b and a plus b to factorize this. So it is going to be k minus 3 minus square root of 12, and k minus 3 plus square root of 12 is bigger or equal to 0. 12 is 4 times 3, so let me simplify this a little bit. Okay, so this is 2 square root of 3, and this is k minus 3 plus 2 square root of 3. This is bigger or equal to 0. If I were to just solve for this quadratic inequality, okay, it is going to have two roots. One root it is going to be at 3 minus 2 square root of 3, and the other one will be 3 plus 2 square root of 3. Substituting values of k into here, here, and here, this is going to be positive, negative, and positive. What I want is for it to be bigger or equal to 0, so it can be this region or this region, which means that k is supposed to be less than or equal to 3 minus 2 square root of 3, or k is supposed to be bigger or equal to 3 plus 2 square root of 3. That means as long as k is within this set of values and this set of values, you'll make sure that this line, it is going to cut this curve at least 1 point. And since this is a horizontal line where k represents the corresponding values of y for that curve also, that is where we can draw our answer from, because the set of values that y can take for this, it is the same as the set of values that k is going to take. So my answer will be that y is less than or equal to 3 minus 2 square root of 3, or y to be bigger or equal to 3 plus 2 square root of 3, and this is the set of values that y can take.